So we come back to herpes simplex, a virus that I told you that despite our immune systems can reactivate from latency, thumb its nose at the immune system, and still reactivate, be asymptomatically shed, or cause recurrent disease. At the heart of how that happens is the fact that herpes simplex virus encodes countermeasures for each of these layers of the immune defenses. So, if we look at interferons, okay, interferons are really one of the big things that viruses target. Basically, viruses are convinced of two things when it comes to the immune system. This isn't just herpes viruses, this is all viruses. They are all collectively very convinced that interferons and T cells need to be counteracted for them to succeed in their life cycle. So again, we talked about the effect of interferon on viral replication and how it could slow replication down. This is basically just a list to illustrate the number of different viruses that encode countermeasures to host interferons. You have Epstein-Barr virus, vaccinia virus, adenovirus, HIV, HSV. They all encode inhibitors of protein kinase R, one of the key mediators of how interferons can shut down viral protein translation. You have other viruses like vaccinia virus that have stolen the interferon alpha beta receptor from our own cells, and the virus infected cell secretes it so it can soak up the cytokine before it finds its target. It just soaks up the hormone so the signal is not delivered. And then there are other proteins that other viruses encode that reverse the effects of interferon. So pox viruses used to cause smallpox, still cause molluscum contagiosum. They are kind of the ultimate example of viruses that don't like cytokines. They make a whole suite of proteins that are decoy receptors that soak up cytokines like interferon gamma and interferon alpha beta. They also make cytokine binding proteins that sort of have the same effect in interleukin 2 and interferon gamma. And then they make their own cytokines, all of these stolen from our cells that turn our own immune response against us. All right, so then we come to not only counteracting the innate immune system with interferons, we come to T cells, another thing that all viruses are convinced is important in getting around. In order to understand how viruses derail T cell recognition and control of viral infection, we need to kind of review how it is that a virus-infected cell presents the proteins or viral proteins to the T cell, and that's shown here.
You remember messenger RNA and new viral proteins being made, essentially to assemble new virions, but something else can happen to those viral proteins. There are host proteins called ubiquitin that can tag these proteins. Once ubiquitin has tagged one of those proteins, it's carried to the proteasome, and the peptide chain is fed into the proteasome, where it's partially digested into shorter peptide fragments. Those shorter fragments now are acted upon by additional peptidase enzymes that are present in the cytoplasm and broken up into smaller peptides. Those peptides now go to the endoplasmic reticulum, gain entry through a molecule called TAP, and once inside the endoplasmic reticulum, if they're the right conformation, they will bind into the binding groove of a developing MHC class 1 molecule. That's the factory worker grabbing a piece of the developing bomb. They're then carried to the cell surface from the endoplasmic reticulum, where they then get embedded into the surface of the cell. And at this point now, they are giving an alert to cytotoxic T cells that something bad is going on inside that cell. It contains foreign protein. Cytotoxic T cell comes along, and if it recognizes foreign viral protein in an MHC class 1 molecule, the T cell receptor on a cytotoxic T cell will be able to directly engage through a conformational recognition along with the CD8 molecule, and that leads to the release of granzymes and perforin that actually kill the virus-infected cell. Now, ideally, you kill the cell before any progeny virions are produced. And in fact, what happens in real life may be quite different. Here you see viruses budding from the cell surface.
All right, so we don't need to go through that any further, but the main point is that for a virus-infected cell to present digested viral proteins or peptides in MHC class 1 is a pretty complex process. There's a lot of steps. And viruses know this, and so they take advantage of it. What the virus-infected cell wants is to make sure that peptide doesn't reach the surface so the CD8 T cell cannot tell the cell's infected. Okay, so it wants to disrupt this recognition. And viruses collectively encode a whole suite of proteins that do nothing but this. I'm going to just show you the proteins that cytomegalovirus uses for this, because it illustrates, how big of a deal this is to viruses. So, and I don't have that presentation open, do I? All right. All right, so here we are. So we have, in the case of cytomegalovirus, a herpes virus, typically infects monocytes and macrophage, and without interfering with this antigen presentation pathway we just talked about, what would happen is CD8 T cells would easily be able to see the cells infected with a foreign virus, and they would kill it, and you would have no lifelong latent infection. So this is a problem for CMV, or cytomegalovirus. As far as how viruses in general can mess with the MHC class 1 pathway, there's all these steps. They can interfere with the proteasome, they can interfere with the transport of peptides into the endoplasmic reticulum through the antigen transporter, TAP. They can retain the MHC class 1 in the endoplasmic reticulum. They can derail these subsequent steps. They can take molecules off the cell surface. All of that can happen. So if we go through examples, Epstein-Barr virus does this first one and inhibits one of those steps. Herpes simplex virus inhibits this TAP transport of peptides. Adenovirus retains MHC class 1 in the ER, and there are other retrafficking strategies that are used by other viruses. Now, if we come to cytomegalovirus, it does all of these because it really doesn't like MHC1. So it has one protein dedicated to messing up the generation of the T cell peptides. It has another cytomegalovirus protein that disrupts the transport of the peptides from the cytoplasm into the endoplasmic reticulum, another protein that retains MHC class 1 in the ER, and in case that fails, two more proteins that prevent the MHC class 1 from ever reaching the cell surface. So, cytomegalovirus is quite good at making sure that MHC class 1 doesn't reach the surface of virus-infected cells through 5 different proteins that counteract each of these steps. The problem is that when cells have no MHC class 1 in their cell surface, they become vulnerable to attack by a different type of cell of the immune system, natural killer cells, that's always going around and checking to make sure cells have MHC class 1 on them. So how does cytomegalovirus deal with this? You have your 5 proteins ripping the MHC class 1 off the cell surface. Cytomegalovirus encodes a decoy protein that looks just like a real MHC class 1 molecule, again, stolen from our cells, and it encodes another decoy molecule that tricks the natural killer cells into saying, okay, there's nothing to see here. 7 viral proteins dedicated to this one task. There are many viruses that exist in nature that don't encode 7 proteins. Okay, so this is a pretty sophisticated strategy, which just illustrates how convinced this virus is, and other viruses are, that T cells are a big deal and they need to get around it. So, yep, this is the same thing I just told you. Examples of individual viral proteins that inhibit each of these steps, basically making it so T cells, cytotoxic T cells, can't see virus-infected cells. So having gone through that, the countermeasures of HSV, let's put it all together in the context, finally, of the biology of recurrent herpes. So the paradox that was raised by physicians in the 1970s and 1980s, before we know all the details, is that, it's strange, but people who experience recurrent herpes often have the highest levels of quote-unquote immunity to HSV. And what they meant is they had really high levels of HSV-specific antibody, which you think would protect these people against getting these recurrences. That's what antibodies are supposed to do. But if you really think about the mechanisms by which the antiviral immune response works, this really isn't that much of a paradox. So here's the reality. First layer of defense, we talked about the 3 hurdles, the interferon-induced antiviral state that could restrict HSV spread. Well, the reality is herpes simplex virus makes a protein that is an antagonist of protein kinase R, one of the fundamental players in the interferon response. What PKR normally does when it's activated is it slaps a phosphate on a cellular factor called eukaryotic initiation factor 2 alpha. Basically, when this protein is normally functioning without the phosphate, that's an essential step of how you get a messenger RNA to be turned into protein. You need that factor around to start the translation machinery translating a messenger RNA. When you put a phosphate on it, that protein translation stops. So PKR activity can shut off viral protein synthesis right when herpes simplex virus is getting to the point where it's ready to make new virions. That would be a problem. Except herpes simplex virus encodes a protein called ISP34.5 that complexes with a cellular protein called protein phosphatase 1, and their job is to cut the phosphates off of EIF2 alpha as fast as PKR can put them on. So with that in place, yeah, okay, you can have PKR and it can try and shut down protein translation, but the virus is just going to inactivate that mechanism of immune resistance. Okay, interferon-induced antiviral state wiped out. So next layer of defense, antibodies. Okay, antibodies could stick to HSV-infected cells and call in the troops, the white blood cells, to attack these cells. Well, HSV-1, like Staphylococcus aureus, makes an Fc gamma receptor. That is a protein that binds to the business end of the antibodies. In this case, it's called glycoprotein E, glycoprotein I, 2 proteins. But together, they bind to the Fc portion of antibodies, and they take the antibodies out of the game. Okay, so all of the humoral immune responses you would want to target these cells for destruction have basically just been neutralized. Now, there is a second layer of humoral immunity called the complement cascade. And if the antibodies could start the complement cascade, that could also pose a problem for the virus-infected cells because they would get coated in a molecule called C3b that would set up a chain reaction. And that would also promote inflammation. But herpes simplex virus encodes a C3b receptor to neutralize this factor so you don't get the complement cascade. So these proteins collectively take out the humoral immune response. So we took out the innate, we took out the humoral, now we're down to cell-mediated immunity, and I think you know where this is going. This virus encodes ICP47, stops up the antigen transporter. MHC class 1 does not efficiently reach the cell surface to present HSV antigens to the T cells. These are not absolute roadblocks. They don't absolutely derail the whole immune response. If they did completely derail the immune response, somebody would die of an HSV1 reactivation. But what they do is they certainly slow down immune recognition of a reactivation event. So basically, recurrent herpes is not really a paradox when you consider that HSV actively obstructs all 3 arms of the antiviral immune response. And so the basic picture that emerges is that this virus, once it's latent, can, at the time it chooses the right stressor, reactivate, make new infectious virions, and create a 2 or 3 day window of opportunity for it to reach the skin and be asymptomatically shed and reach the next person, which explains why 4 billion people on Earth are infected with HSV1 or HSV2, or both. And this is basically what I was talking about. So what the seroprevalence data says is roughly about 2/3 of people in the United States are infected with HSV1, and about somewhere between 1/10 and 1/6 are infected with HSV2. Although these are extraordinarily common infections, most of the infections are asymptomatic. That is, the immune system does its job and controls it. People who live with high-level symptoms of recurrent herpes, we're usually talking about 1 or 2% of the total number of people infected. That doesn't sound like a lot, but when 4 billion people are walking around with HSV1 or 2, that means that somewhere around 100 million people on Earth are suffering with some form of recurrent herpetic disease that keeps coming back. So, key features are alpha herpes virus persistent. The latent state allows the virus to maintain a stable reservoir of several thousand latently infected neurons. The virus can hide out there as long as it wants. This is not only true of the alpha herpes virus, this is also true of things like cytomegalovirus and Epstein-Barr virus, that is the beta and gamma herpes viruses. and immune evasion. So the latency explains the stability of the reservoir, the fact that once it's established, it doesn't go away, it remains for life. The immune evasion properties explain how it is that a latent infection can, in a person who's got a good immune response, still promote transmission after a reactivation event. So reactivation is basically a low-level or single-cell reawakening of herpes viral replication in the case of HSV 1 or 2 in a single neuron, and the immune evasion proteins create the window of time necessary to delay immune recognition long enough that the virions can reach the surface of the skin and be transmitted to the next person, which again explains how 4 billion people are infected with these viruses. So, take-home message of the whole lecture. Microbes that persist in the human body typically employ one or more of these strategies that we reviewed in the beginning to do so. And those microbes that persist establish latent infections that are typically described by clinicians as chronic, that is high-level replication like happens with HIV and hepatitis C, even in someone who is clinically asymptomatic, versus episodic disease, such as you see in malaria, where somebody will get recurrent disease every 3 or 4 days, versus latent infections like the herpes viruses that only infrequently recur, and in some people might only recur once in a lifetime or never. Okay, so those are the 3 flavors of persistent infections. And maybe the most important thing that any future doctor should know is what is the difference between true love and herpes. And here you see Nancy and Sluggo hanging out on the bench, enjoying their moment of true love, and here's herpes virus. What's the difference between true love and herpes? Herpes is forever because it evades the immune system.